So for this lecture, number 27 over section 10.8, we are going to introduce our last concept in statics. Yay, the mass moment of inertia. It's kind of similar to what we've been doing with the area moment of inertia. It's just that now we're going to be working in 3 dimensions. So we're going to talk about what the mass moment of inertia is, and then we're going to talk about how to calculate it for a composite body. So there are a couple different applications here. I didn't really talk about applications last time, but really the application for a mass moment of inertia is that when we talk about the mass moment of inertia, we're looking at something's resistance to angular acceleration or rotational movement. So it can help with any of these pieces that move in a circular pattern. So let's start with our notes. Mass moment of inertia. The mass moment of inertia, so we'll start with that, the mass moment of inertia. Sometimes people call it the MMOI, is a property that measures the resistance of the body to angular acceleration. So we have a picture to the right where it shows the mass moment of inertia about the z-axis for this particular particle is going to be I is the integral of the mass of r squared times the differential mass. So we've just got the differential mass, so we're integrating over the mass as a whole, where r is the perpendicular distance from the axis to any arbitrary element dm. The mass moment of inertia is always a positive quantity and has units of kilogram.meters squared or slug.feet squared. So the tables that you got in prior classes has these simple shaped areas that we're going to be working with in 3 dimensions. And you can see it's got the mass moment of inertia is listed at the bottom where it's got I about the xx axis, the yy axis, or the zz axis. And you can see, depending on what we're trying to calculate it about, which axis we're going to use and which equation. Just as with the moment of inertia for an area, the parallel axis theorem can be used to find the mass moment of inertia about a parallel axis z prime that is a distance d from the z-axis through the body's center of mass. The formula is that I about the z-axis equals ig plus md squared, just like the parallel axis theorem, only now we're using mass times a distance squared, where m is the mass of the body. And finally, the mass moment of inertia can be found using the method we've seen before for a composite body. So I think next we start on some examples. So the first example we have is this plate that's shown. It tells us what its density is, which is going to matter when we start talking about calculating volume. So it's got a density and how thick it is. It wants to know its mass moment of inertia about an axis perpendicular to the page and passing through the pin at O. So what I'm going to do is I'm going to use 2 different circles, discs. I'm going to take discs that we have the equations for, and I'm going to use an outside one and an inside one. And I'm going to subtract the smaller distance from the bigger distance. So I'm going to move these out. So I've got the bigger distance, and then I've got the smaller circle. So I'm going to call this one A, and this one B. And so we know from our tables that for a circular disk, and look at the point it's trying to rotate about this point O that's on the outside. So it's about this point O is right here where we're looking at. So when you look at your tables, notice that for a circular disk, I of G equals 1/2 the mass times the radius squared. And so for what we know, we're going to calculate our mass moment of inertia is going to be that, plus we need to use the parallel axis theorem. So we're a little bit away from the axis. O is a little bit off the axis. So we're going to start our nice handy dandy table. So we always start with what part we're using. Then we're going to need to calculate the volume of the disk. And with the volume, we can then use its density, which is up here listed as 8,000 kilograms per meter cubed. So we can use that to find its mass. And then we need to know its radius, its distance d from the centroid. And then we're going to calculate the I of G. And then we're going to finally finish with the I of O using the parallel axis theorem. So let's start with our first part. So we're going to start with part A. The volume of a disk is going to be, just like we used in the prior information, is going to be the area of the circle, so pi times the radius, which in this case is 0.25 squared, times the thickness, which it tells us the thickness is 10 millimeters, which is 0.1 meters. When I calculate that out, that is 0.0019635. To get the mass, I'm going to multiply the volume by 8,000 kilograms per meter cubed, and that's going to give me a mass of 15.708. My radius I can find, because that is the distance away from O. Its centroid is 0.25 is its radius, but its distance is also 0.25 from O. So I of G, I'm going to take 1/2 the mass times the radius squared. So I plug that into my calculator. I get 0.4908739. And then I add to that the mass times the distance squared, and I get 1.472624. Now I'm going to do it for part B. Now remember, part B is negative because I'm taking that away. So my volume is going to be negative. So it's going to be negative pi times its radius, which is 0.125 squared, times its thickness, which is 0.1. And that gives me negative 0.0004987, which I multiplied by 8,000. That's its density. I'm going to get negative 3.92699. Now note that its radius is 0.125, but its distance from its centroid to point O is still 0.25 to get to point O. So that's its distance, because we're using the parallel axis theorem. So we're looking at as if it is going through the centroid at G, but we're calculating it for O. So that's what we need to use our distance for, how far away O is. So I of G, I'm going to plug it into my calculator. I'm going to plug in 1/2 times mr squared, which is going to give me a negative number. It's going to be negative 0.06796. And when I add to that the mass, which is negative times the distance squared, I still get a negative number, negative 0.2761165. I then add those together, and I get that my final mass moment of inertia is 1.196 kilogram dot meters squared. Yay. All right, let's do another example. This example has a pendulum consisting of two thin rods that each weigh 10 pounds. Notice that it's giving me the weight, which is a force, not the mass. So I'm going to have to find the mass in order to get the equation. So I'm going to draw these two plates. So I've got one bar here, and then I've got one bar here. So I should have done this before. I apologize. All right, here's my two bars that I'm going to break it down into. Notice that it wants the mass moment of inertia about point O, which is up here at the top. Determine the pendulum's mass moment of inertia about an axis passing through the pin at O. So I'm going to say this is A, this is B. And so I'm going to have to calculate the mass. To find the mass in imperial units is in slugs. So I've been given pounds. To find slugs from pounds, I'm going to have to divide by G, which equals 32.2 feet per second squared. So that's how I'm going to find the mass. So I'm going to take the 10 pounds, I'm going to divide by 32.2. For a slender rod from my tables, these are two slender rods, so I need the I of G for a slender rod from my tables. That is 1/12 of the mass times the length squared. So I'm going to need to know the length of each. I also need to know the distance from the centroid of each to point O. So I'm going to have my part, make my table. I'm going to need to know the mass. I need to know the length, to know the distance to point O. Then I can calculate I of G. And with I of G, I can get my I of O. Those are all the parts I need to get my total mass moment of inertia. So I'm going to start with part A. The mass of part A is 10 pounds over 32.2, which equals 0.310559. Now length, if I look at how long it is, it shows me that it is 2 feet long. The distance from point O to its centroid, it is half of 2. Because its centroid is going to be at half of 2, so half of 2 away, which equals 1. So now I can do I of G, which is 1/12 ml squared. So 1/12 of m, which is 0.310559, and L squared is 2, which equals 0.1035197, Now, if I do, remember I of O is, we're using our parallel axis theorem, plus md squared. So when I add md squared, I'm going to get 0.41407787. All right, let's do part B. Its mass is going to be the same because it is also 10 pounds is its weight, so it equals 0.310559. It is also 2 feet long, but its distance is going to be 2, that whole length, 2 feet from point O. So I of G is going to be 1/12 times the mass, 0.310559 times its length, which is 2 squared, so it's going to be the same as the one above, 0.10351967. But when I add the mass times the distance squared, the distance is further, so it's going to be greater. So it's 1.345757. So I get a total, I of O equals 1.7598 slug dot feet squared. Slug. Always makes me laugh to say slug. Sounds like it is some kind of worm. All right, our last example problem that I have for you is a pendulum that has a plate on the end that has a weight of 12 pounds. So once again, we're going to have to find the mass. And it has a slender rod with a weight of 4 pounds. Determine the pendulum's mass moment of inertia about an axis passing through point O. So I am going to label these as part A is my rod, part B is my plate. And remember that the mass equals the weight over gravity, which in this case is 32.2 feet per second squared. And if we look in our tables, we get for a thin plate, I of G equals 1/12 of the mass times A squared plus B squared. And for a slender rod, I of G equals 1/12 the mass times the length squared. And remember that IO equals IG plus MD squared, where D is the distance from the axis we're going to. So it's going to be from the centroid to O. All right, so we've got our part, its weight, and from that I can calculate its mass. And I need either an A or L, so I'm going to call this A and B or L, depending on what I need it. Then I need the distance from the centroid to O. Then I need to calculate I of G from the formula, and then I need to calculate I of O. All right, so part A, its weight is 4 pounds, which divide that by 32.2, I'm going to get 0.1242236. And its length is 5 feet. its distance is from O is going to be 3 minus 1/2 of 5, which it is only 0.5 feet away from the axis passing through O. And then I of G for a slender rod is 1/12 times the mass, 0.124 times the length squared, times 5 squared, which equals 0.258799. And when I add mass times the distance squared, I'm going to get 0.2898551. Then I'm going to do part B, which it told me was 12 pounds. So divide that by 32.2, you get 0.372678. And its A and B are both 1. Now its distance is going to be that 3 feet plus half of one side, which is 1, which equals 3.5. Its I of G is 1/12 times the mass, 0.373, times 1 squared plus 1 squared, which equals 0.062112. And when I add the mass times the distance squared, I get 4.6273292. When I sum those both together, I get that I of O equals 4.917 slug dot feet squared. All right, I hope this made sense. Good luck.